So I use the clickers a lot in class, and something akin to peer instruction that you'll hear more about, I take it later. And so for that example, I'd ask a question along the lines of, I throw a ball into the air, it rises, pauses momentarily, and drops back to my hand. Describe which of the following describes the acceleration best as a function of time. And the choice would be something like, well, it's negative the entire time, or it's pointing downward the entire time. It's pointing downward and then is 0 and then points downward again. Or it points downward, it's 0 and then points upward, right? Some combination of those sorts of things. It's very conceptual, right? I'm not asking them to put numbers on it or anything like that. And that clicker question is posed to them. They're supposed to answer it on their own individually. They put those in. I will often go through a second round. So in peer instruction, you're often using the second round to try to get the better students to teach the other ones. But sometimes for listing the misconceptions, it actually works to use that second discussion period to help them really bring their misconception to the fore. In other words, they're trying to convince another student that their misconception's right. Right? And so they discuss it, they'll vote again, they have the histogram of answers. And then for that one, it's largely a matter, I don't have the technology readily available in the classroom to show them that the acceleration's not 0 at the top, right? The time resolution isn't there, these sorts of things. So it's a matter of then walking them through seeing that it's not 0 at the top, right? We go through the process of, all right, draw me a graph of the velocity as a function of time. And as they do that, make sure everybody gets that right and they see it's just a straight line. The only thing special about that turning point is that the velocity crosses through 0. The slope of it never changed. And then, well, how's acceleration related to velocity? It's the slope. So what would you plot for acceleration as a function of time? And it's a straight line, the same constant value the whole time. That works for most of the students. There'll usually be some questions that come out of it, sort of using the clickers and discussions to get them to elicit their misconceptions, makes them much more willing to ask questions later when they realize the misconception existed. And so there'll be a few who still, I don't see it. I don't see how it's 0 at the top. And so then it works to work through some sort of example, say, okay, suppose the ball was at the top and it had 0 velocity momentarily. We all agree on that. And it had 0 acceleration. Let's take that and see if it works. What would happen to the ball in the next moment of time? Well, if the acceleration's 0, the velocity is going to stay 0. And if the acceleration's still 0 because it's paused, it'll stay 0. So if the acceleration were 0 at the top, the ball would just stay there, right? Now, the more sophisticated students will realize, well, maybe acceleration itself could change with time, right? You could have some jerk to the system. But that works as a reasonable explanation for most of them. My favorite way to tackle the misconceptions, and it doesn't work for all of them, is to have a clicker question that asks them about some particular situation that elicits the misconception, and then to have a specific demo that shows them that their answer wasn't correct, instead of me just telling them that the answer wasn't correct. And so one of the ones I do that for is having them realize what tension in a string really means. And so the setup for that is that we have a lecture table in front of the classroom, and there's a post standing in the middle of it. And off of that post, there is a string, a spring scale, a string coming off the other end, goes over a pulley, and you got a weight hanging from the side of it here. And you hang a half a kilogram weight there, and the scale weight reads 5 newtons. They're all comfortable with that. We walk through why that's true, and they can see it. And so then the clicker question is, all right, suppose I then replace this post, take the string off that post, continue it over the end of the table off another pulley, and hang another half kilogram weight there. So I have 2 kilogram weights, strings coming up to the middle, and the spring scale's in the middle. What's the spring scale going to read now under this second circumstance? And the same process, students try it on their own, and then after they put in those answers, They go back and they discuss with their neighbors and try to convince one another of what's right, and you see the histogram shift around a little bit. And the answer choices there are something like 0 newtons, 5 newtons, 10 newtons, and maybe there's 1 or 2 others thrown in there, right? Those are the important ones. Right. 5 newtons is the right answer, but probably only about 5% of the students ever say that. The overwhelming majority go into 2 camps. They say it's either 0 newtons, invoking some sort of the spring is at equilibrium, therefore there are equal and opposite forces on both sides of it, they cancel, and it will read nothing. Or 10 newtons, we have twice the weight, it must read twice the value now. And I mean, maybe it's, well, I take real pleasure in then showing them the demo. And quite frankly, the mouths of the people in the front row, they can see the scale. They can see when I drop the weight on the other side that it still says 5 newtons. And their mouths just gape open. They don't understand how it can say 5 newtons. They've convinced themselves that it should be 0 or 10. They've talked to their neighbors. They've all reached consensus that it's got to be one of those answers, and it's not. And so now they're very willing to start asking questions. Why is that? What does tension really mean? How are you describing the forces and how they balance here, and how does that give you 5 newtons? And it just creates a really rich discussion in the classroom, and hopefully something that sticks in the students' minds as they go forward from there, right? I'll have them over the next week keep coming to me at office hours and at the help desk asking, I didn't quite get it, can you explain some more? And I think eventually it sinks in, but it's powerful to be able to do an explicit showing them that the misconception was there. I think it's important from the very beginning of the semester to let the students know that you're aware they're going to have misconceptions and that you're going to be trying to elicit them, that they shouldn't be ashamed of, that this is a low-risk environment, right? That mistakes are encouraged and allowed and they'll learn from them, that their experience to this point, especially for physics, they know more physics than they think they know just from having lived on the Earth for 20 years. But a lot of the physics they think they know isn't quite right because it's specific for one environment and we're trying to generalize it. I often tell them there's a great Mark Twain quote, right? It's not what you know it's not what you don't know that hurts you, it's what you know that ain't so, right? And so set them up for that from the very beginning and let them know that that's the way the class is going to run for the semester. Now, one of the reasons these things are difficult to change is that the students have a tendency to very much compartmentalize their knowledge. And you ask them a question, and you're like, do you want the answer for physics class, or do you want what I really think? And they can easily separate that, and they have that dichotomy in their heads. And we want to try to bring them together to actually change their beliefs about the way the world works in some sense, right? It's subversive. That's what we are being a bit subversive. We don't want them to have one set of knowledge for physics class and one set of knowledge for the rest of what they do. And so I think this has worked in a sense that we use there's some nationally normed assessments. The Force Concept Inventory works for physics, the first semester of it. And so we give that as a pre-test. It's a 30-question test. We see how students do on it. Average for our students is they get about 13 out of the 30 right coming in. But there's a wide range, right? Some of the students get 2 or 3 right. Some of the students get 27, 28 right out of 30. Then, at the end of the semester of instruction, we give them the exact same test again, although then we didn't tell them they were going to take it again. And we measure how much they improved. And how much they improved is based on sort of a normalized gain. So if they got 10 right at the start of the semester, then there were 20 more questions they could have gotten right. And if they get an additional 10 right at the end of the semester, well, they had a gain of 50% of what they could have possibly learned in the classroom. Physics education research did a lot of work on that, and it showed that from high school to Harvard, the numbers for traditional lecture were about 23% gains in what students learned. We've been consistently getting over 50% gains. So we're very happy with that. It shows that some of this is sinking in and staying, even when they think it's not a physics class anymore. So.